Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 6 a.m. on Saturday in Germany. We're broadcasting live from Thousand Oaks, California. Tonight, we have a crunchy topic, Neutron Stars. We'll be back in 8.3 seconds. We've talked about several different types of stars. Some aren't actually stars. Tonight, Jeff will talk about neutron stars, which, like white dwarfs, are actually the remnants of stars rather than stars themselves. He will also talk about why protons and electrons haven't already collided and become neutrons. If they had, we wouldn't have atoms or even us. It's rather convenient that they didn't do that. Jeff, take it away.
Okay.
Are we sharing?
Yeah. Hey, Dawn.
Oh,
yes.
Hi, Dawn. Oh, let me go over there now. There she is.
I guess I'll share.
Welcome. Glad you're here. Yeah.
It's okay.
Hard to do two things
Neutron
at once.
Stars. There we go.
Some nice graphics.
Yeah.
I don't think there's any actual pictures, are there?
No, because they're really far away.
Yeah. They're kind of small, aren't they?
Really small.
Okay. Oh, hello, Scott.
In fact, I'll show that a little bit.
Loves the crunchies.
Yeah.
Yeah, we do too.
Yeah. So I just wanted to lead off with some pictures.
Very nice pictures too.
Mm-hmm. And this is I'm going to give a bunch of links too. This is a NASA. NASA has some pretty good details on various
cool
things. Not the most complete, but it's pretty darn good. One of the things is that a neutron star, which has about 1.5 times the mass of the Earth, of the sun, of our sun, is only about 12 miles across.
So pretty small, but they're bright, right?
They're bright in X-rays a lot of the times, and in magnetic fields and stuff like that. Not visually bright so much.
Okay. And we actually ran an Anton, and he was talking about neutron stars too. That was right before we did our show tonight.
Yeah.
Yeah, he actually talked about them being a little bit bigger than that, I thought.
Well, no, mass wise, they're fairly big, but
okay.
And no, he used kilometers, not miles. So they're
no, he was talking about solar masses, like couple instead of one.
Yeah,
1 point whatever.
The biggest,
still pretty small.
And we'll get into that. The wiki has all of the numbers, but
okay,
it goes up to like 2.3 solar masses is the biggest it can be before it gets too big to hold its shape, and then it collapses into a black hole.
Okay.
So basically about 1.1 solar masses to about 2.3 solar masses is a neutron star. Smaller than that, and it doesn't have enough crunch to make it a neutron star. It remains a white dwarf.
Okay.
And now that in the 1.1 to 2.3 solar masses is not the mass of the star that created it, though. It's just the mass of the
what's left
of the core. Yeah, what didn't get blown off. It's actually a 10 to 15 solar mass star that becomes a neutron star.
So what happened? A nova, supernova?
Yeah, supernova.
Supernova.
Just,
so most of it just blew off, and now we've got this core left. Okay.
Right. Yeah. Yeah. The shock wave of the big crunch after the fusion stops, then causes the outer layers of the crunch to blow off.
Okay.
And because it generates a great amount of heat when it crunches, so the outer parts blow off. And if it's small enough, it becomes a white dwarf. If it's big enough, it becomes a neutron star. If it's super big, it crunches down to
black hole, right?
Yeah.
Okay.
Yeah.
All right. And I noticed you talked about the NASA sites, and there's a lot of good stuff on NASA. I mean,
oh yeah,
I wouldn't knock it.
Yeah. When I first started thinking of these, I was thinking that I'm not going to be talking too much about the neutron stars because they're not very complicated. You know, it's a bunch of neutrons. I kind of, if you can see along the top of the screen there's a bunch of tabs. So
lots of tabs.
Yeah.
Good. Okay.
Okay.
So you found out something else. Good.
Yeah. Now, the main thing when I've thought of neutron stars and the fact that the electrons collapse into the protons and thus form a neutron, made me wonder why protons don't just do that.
Mm-hmm.
You know, okay, one could argue that, you know, that when the universe was cooling in the initial moments after the Big Bang, that those who hit the protons became neutrons, and what's left are the ones that just happen to hit an orbit. Wrong.
Okay.
For one thing, electrons don't actually orbit.
They're sort of in a fuzzy thing, a cloud of.
Yeah, it's the probability of the electron being there.
A probability field, I think it's called,
Yeah.
right? Yeah.
And
oh, you got something?
Yeah. Here.
And
here we go.
Wrong. But it's so cool looking.
Yeah, but it's wrong.
Okay.
The trouble is that, and the reason why you get what they call electron shells is because the mass, because the kinetic energy of the electron actually gets higher as it gets closer to the proton. So the closer to the proton it gets, the faster it's moving. Therefore, the less chance of it being there.
Okay.
Because, you know, think of, you know, things that are zipping, you know.
Yes.
You know, it's in an area where it's moving slower, it has more chance of being there.
Okay.
And of course, too far away, because the electron or the proton does attract it. So too far away, there's less chance of it being there. So there's a bell curve of where it might be.
Okay.
And there's also the probability of, since as you get smaller, the volume is smaller.
Okay.
So there's less chance, there's less volume for it to be in.
Okay.
So you end up with a sweet spot, and this is.
Oops, wait, let me go back.
Oh, okay.
There you are.
Okay. Here we go.
That's the thing about particle physics. It's so fascinating.
Yeah. So this is where it's likely to be, you know, just in relation to the proton itself.
Can you bigify that picture some?
Only a little. There we go.
That's better.
Just basically, since positive attracts negative, it's more likely to be here than out here. But as we get close, hang on. This isn't the one that this isn't the best one. I don't have it. Okay, but here we go, right here. This is the probability density of it being in a specific location.
Okay.
And this is what the bell curve looks like. Now, once this field here, I don't know if you can see my mouse pointer, but once this green ring here is filled.
Sort of not the innermost, but the middle one.
Yeah, well, this is the nucleus.
Okay.
The orange is the nucleus.
Okay.
So once this green ring is essentially filled, there's enough electrons because they repel each other. Then there's another ring that'll appear outside it, which is the next most likely spot for them to be in.
Okay.
And that's how we get the electron shells. It's not because they're orbiting at different distances. It's just that now, and here.
That's very different than
yes.
I remember being taught.
Yes, exactly.
Okay.
Well,
and that's, you find out a lot of things after you're in school, and
I
it's like, wait a minute,
I have a problem with the way I was taught physics in school too.
Yeah.
Because they kept teaching us the wrong thing, and then they'd say, but this is the way it really is. Why did you tell me the wrong thing then?
Yeah.
You know, we spent an entire semester going from
let's just skip that stuff.
Yeah, let's just skip the wrong stuff and let's get to what really is.
I could see if there's an actual purpose for it, but
yeah,
didn't seem like it.
It showed the evolution of the theory, but
Ah.
I didn't care about that. I wanted to know what is. But so now we know why, because I was wondering, if you've got a plasma, you've separated out the electrons and protons.
Okay.
And when it cools, why do they suddenly snap back into orbits,
Yeah.
instead of just, oh, positive, negative, they should hit each other and merge. But this is why, because as it cools, they fall into this pattern again. And what a neutron star does is its gravity is its pressure is so high in it that it actually, the repulsion from the other electrons pushes the electrons closer to the nucleus. It's able to, even though kinetic energy goes up as it gets closer to the center, the pressure on it overcomes that. And the electrons pack closer and closer. And it's not like they're being pushed. It's just they're more likely to be there.
Trying to think of a good example that,
yeah,
like you can talk about the expanding universe and talk about bread and how gets those holes get bigger. But what about this one where they're
now when the most probable
coming to mind yet?
Now when the most probable location for an electron to be is inside the proton, there's a fairly high chance that it just basically merges with the proton and boom, now it's a neutron.
Okay.
There's always a chance that it doesn't, though.
Okay. Particle physics are weird, yeah.
Yeah, because you get into quantum dynamic stuff.
Yep.
And which also means that a neutron star is not as homogeneous as I had thought.
Oh, okay.
There's a lot going on in a neutron star.
Okay. You ready to show us that?
Hang on, let me find
a
good image. Okay, here's a good image.
All right, let me share. There you go.
Okay, so here is a good theory as to what a neutron star looks like. And here,
so the bottom one there, right?
Well, the top one is shows
like a 3D version of it.
Yeah.
Okay.
But let's make this a bit bigger.
Okay, good.
Okay, so you've got a crust, and I'll talk about that later. But
right, yeah.
Apparently, when a neutron star just forms, it's just this massive stuff. But as it cools, a crust can form, and there's kind
like
of
an actual crust.
Yes, a crust made out of, because it's crushed so much by pressure, the crust is actually solidified helium and hydrogen.
Crystalline, maybe, or
I don't think so.
By pressure, or
if it's crystalline, it's very fractured crystalline, I think. But so this crust forms, and then you've got neutron liquid inside that.
Let me go back there.
Yeah. So
there you go.
These are just a mass of neutrons, and it's actually more complicated than even this. Then there's this core here. Let's see. There's another image of what they think it looks like. Oh, and this is a neutron star versus Frankfurt.
Yep.
I mean, that's,
much heavier though.
Yeah.
Much more dense.
Yeah. And here, let's see. This is oh yeah, neutron star versus Chicago.
Okay.
And this is actually the image that got me realizing that neutron stars. Now, so this is, there's actually an atmosphere around it too.
Okay.
Now the atmosphere is measured in micrometers thick.
Okay.
So take thousandths of a millimeter. That's how tall the atmosphere is.
Still an atmosphere.
Yeah. And the crust.
Who would have thunk?
Right.
Yeah.
And the atmosphere is hydrogen, helium, and apparently some carbon.
Good stuff.
But,
no.
Yeah. And the crust can actually fracture. Yeah. The crust can fracture, but because of the high gravity and high pressure, or the high gravity, the biggest surface deformation on the crust is 1 millimeter tall.
Okay.
So it's one of the smoothest things out there. Because nothing higher than a millimeter can actually survive it. Basically, would push down and push the other stuff out of the way, and
It's a
flatten.
gravity thing, I take
It's a
it.
gravity
Okay.
thing. Yes.
All right.
Yeah, it's kind of like where Mars can have that really big volcano, mountain, because it doesn't have as much gravity.
Got it. Okay. Just
So
in the other direction.
yeah, yeah.
That's a neat. That's a neat image. You want to tell us some more about that?
Just more. This is more detail about what they think it is. Now, this neutron superfluid, and this is the transition layer between them, between these two layers, is that it's not a sharp cutoff, but it kind of blends in there.
Okay.
That and this neutron fluid actually does have electrons and protons in it.
That's kind of more blue in there, right?
Yeah, the blue. It has electrons and protons in it, but not very many.
Okay.
And as you go down, you get more and more neutrons clumped together. So you have atoms, you have neutron atoms,
Okay.
with them clumped together to the point where you can have hundreds of neutrons clumped together, and they don't break apart as they, if you tried that outside of a neutron star, it would fission.
Okay.
Just basically because the internal pressure of it would just cause it to burst. But there's so much gravity that they can't do that.
Okay.
So they actually call it a neutron drip, as free neutrons, because they make a distinction between free neutrons and neutrons that are bound into nuclei, I guess, even though they're the nuclei of nothing. I mean, they're just clumps.
Okay.
And inside, in the inner core, there are several different theories about what's in the inner core, because no one really knows. Some think that it's, just one theory is that it's just a solid pack of neutrons. Another one thinks that it's that they've broken slightly and it's a quark soup. So the neutrons themselves have broken down, but there's still enough pressure of the quarks to keep everything still, not totally collapsed into a black hole. But there could be a quark soup in there. They're thinking that for the biggest neutron stars.
Okay.
In fact, there's kind of a mass anomaly where the smallest black holes are actually bigger than the biggest neutron stars. So there's a gap there that either nothing can fall into it or things do, and we don't know what it is.
Yeah, I think that's what Anton was talking about, and a mass gap.
And one of the possibilities
MASS.
is a quark star.
Okay.
Just basically it's a bunch of quarks now instead of neutrons. So but apparently if there is, we can't see it.
Okay.
I mean, we could possibly work out the mathematics to say, here's the number of neutron stars, here's the number of black holes. And by the number of stars being produced, there should be X number of something in between. Someone might be able to do that math. As far as I know, no one has.
Okay.
It's right now just there's a gap and we don't know. Lots of ideas, but
and
no.
Things keep getting reclassified. I mean, once when I was a kid, Pluto was a planet, and now it's not.
Oh, heck.
It's.
Yeah.
I mean, that's how things get changed all the time.
Right.
I mean,
but in this case,
pick a topic, and
yeah,
things can be.
Yeah.
I remember talking about music. I remember they would call it heavy metal, but it's just rock and roll now.
Yeah. You don't.
You ready?
No, not yet.
Okay. He's looking.
Yeah. I'm just. Oh, yeah. Here's.
Now?
Yeah.
There's the quark core.
Yeah. So mass of the core. So this is one of the theories that it has a core of quarks.
That's the green there. Okay.
Yeah. And they're saying that, these might be the ones that have it, the ones that are lower mass. This is the radius of the quark core.
This looks a little bit like an HR diagram for these particular.
Yeah.
Okay.
But this is I can't even call this a theory.
Okay.
Because they don't have a way of testing it. These are ideas at this point. Hypotheses.
Well, that's the thing about theories. At some point, they might be testable.
Right.
So,
But,
yeah.
you know, so this is just one of the ideas that they have. And so I just, and then here is the big old, oh, it was 10 and 25 solar masses is a neutron star. I said 10 and 15 earlier. I just forgot because I wasn't looking at this page when I said it.
Got it. That's a neat picture.
Oh, this, yeah.
Wow.
They have a lot of neat pictures in here. They just superimposed this on a,
okay.
oh, or no, that basically this is the neutron star that's at the center of that nebula.
Okay.
And probably different images interposed.
We have a comment. Thomas Holmes.
Yeah.
I believe you're a first-time visitor. Thank you so much for being here and for your question. An odd thought: can neutron stars be considered black holes that never realize their full potential in their life as stars? Underachievers?
Kind of.
That's great.
Kind of, sort of. But then you could also think of white dwarfs as that too. It's just, yeah, I mean, it's amusing to think of it that way, but it's more along the lines of, you know, different categories become different things.
Yeah, and I have a feeling every single thing out there is going to be its own unique whatever.
Right.
Yeah, like every one of us.
Categories, but it's kind of like brown dwarfs could be considered stars that, you know, that are underachievers. That's actually much closer to for your.
So they didn't quite.
Yeah, they
fuse, did. Right?
Right.
Yeah.
Yeah. So, but that gap means that there could be something else out there, like a total quark star or something even more exotic, maybe.
Thank you, Thomas.
Don't know.
We love that kind of question.
But and here, neutron stars rotate, or most of them do.
Okay.
And they do it very quickly. You know, basically because you've got all this mass of a star that rotates shrunk down into 20-kilometer radius, you know, 12 and a half mile radius.
Oh, and I see there on the screen. Do you want me to show it? It says conservation of angular momentum. And this is the skater.
Yeah.
Go ahead and highlight that part.
Okay, yeah.
Like the skater who brings their arms in.
Mm-hmm. Oops.
They're going to go faster and faster.
Right. To the point where 716 times per second rotation.
Okay.
That's the fastest known neutron star.
Okay. That's pretty fast.
Yeah. And spinning neutron stars are, you know, known as pulsars if they're pointed in the right direction. Because if the beam doesn't sweep over us, then we don't see it.
Right. We can't tell.
Yeah. So we can detect them other ways, but we don't get the pulses. But some of them are flashing us 716 times a second. That's really fast spin, especially when you consider the size of the thing and how much mass it has. That's a lot of kinetic energy.
Yep.
In there.
Might make a good engine. If you can harness it.
Yeah. Okay. Yeah. I'll keep one of those in my back pocket.
Get close.
Yeah. Getting close involves becoming paint on it.
Okay.
Now.
I didn't mean that close.
Now they do have really massive.
Oh, let me go back.
Fields.
Hold on.
Oh no, not yet. Okay.
Oh, not yet.
Okay.
Sorry.
Oh, this. Okay, you can go.
You
back
ready?
Here. Yeah, this is just a.
Okay.
The wiki in this case actually is really, really good.
Oh, good.
Some wikis aren't so great.
Some are better than others. It's true.
I could have done the entire show on this wiki practically.
Nice.
Not quite, but practically. But I didn't want to just read off the wiki to you. But this is their. This is how a neutron star is made. Here, let's get this a little bit bigger.
Okay.
And simplified representation: massive star core, inner core implodes under gravity. Gravity smashes electrons and protons together, and we talked about that in a bit more detail than this, releasing a shower of neutrinos, which are simply fast-moving neutrons.
Okay.
Outer layers slosh violently, from the shock of and instability. Outer layers implode and collapse onto the inner core at 25% the speed of light.
Wow.
And then they bounce off the dense core, creating the supernova, which leaves just the...
They bounce off the dense core.
Okay. Well, okay, what happens is that they get so hot that it explodes. Yeah, so the surface, the part that actually hits the core is crushed so badly that it essentially does a fusion reaction and blows the rest of it off.
Oh, okay. Interesting.
So they said that this is simplified, and it is very. So I just added a little bit more detail.
Back to the
mass and temperature.
Wait, am I going back there?
No,
not yet.
I'm just looking. Magnetic field.
Magnetic field. You ready?
Yeah.
All right, there I shared.
Okay. The magnetic field strength on the surface of a neutron star ranges from about 10.4 to 10 to the 4th to 10 to the 11th Tesla.
I don't even know what that means.
Okay. In comparison, a 16 Tesla field has been achieved in a laboratory.
Okay.
So, 10 to the 4 is 10,000. And that's what they consider minimum for them.
Got it.
And we've achieved 16.
16. Not even 8,000.
Right, yeah.
I meant to do this. Let me go back to that. There you go.
So that's, that's huge. And it means that if the gravity doesn't get you, the radiation will you're going to get microwaved, essentially, by the magnetic field.
Don't want to get that close either.
Right, yeah. Yeah, this is one of the things that you don't want to get too close to.
No.
The gravity is on the surface is 2 times 10 to the 11 stronger than the Earth. So 2 times 10 to the 11 G's.
Hey, Thomas says, fun for the magnet. Maybe not so much for the frog.
Yeah.
Thank you, Thomas.
So.
Yes, right.
Yeah, it's and it's so strong that it does act as a gravitational lens.
Right.
They have seen gravitational lensing around them. Such that the normally invisible rear surface becomes visible.
The rear surface of the star itself.
Yes.
Or yeah.
Neutron
star.
And
neutron
we call
remnant.
it a neutron star, but it is actually just a remnant of a star. It's not because there's no fusion happening.
Why do we call so many things stars that aren't?
Yeah. Well, because they're dead stars.
Okay.
But like a white dwarf, a neutron star is not producing any more energy.
Okay.
It's just radiating energy.
Okay.
Now, occasionally there's a bit of a glitch. And, the crust can break and shift. And they call that, a neutron star quake.
Oh, okay.
And
yes, I remember
they
seeing
can
the words.
detect it because the very fast spin sometimes glitches. Because the crust breaking essentially disrupted the spin a little bit, kind of made it shake or wobble. And so the spin still is fast. It's just that it wobbled it enough that maybe, we caught it a little bit faster or slower for that one cycle. So that's some of the fun what's happening on a neutron star.
Just imagine what the kinds of things we're going to learn over time.
Right. And one of the things is that there could.
Am I sure? No. Okay.
There could be planets around a neutron star.
Okay. Even after the.
Well, one of the things that they say might be likely are the cores of gas giants.
Okay.
Might be dense enough and far enough out that they survived the supernova. The other possibility is just after the supernova, enough matter still being around that it forms a essentially a planetary disk and new planets form.
Okay.
Of course, the chance of them having any kind of life on them is kind of small, for one thing. Neutron star does not produce a lot of light.
Yeah.
It does produce some, but
The
not
magnetic
much.
field sounds rough.
Yeah. I mean, so, the things that would induce life into, being. Now, would the magnetic field produce enough energy on the surface of a planet to maybe be something that chemicals could absorb and thus replicate and thus form another type of life? Kind of a, a virus or prion, type of chemical that absorbs this kind of energy rather than solar chemical, So it's possible. I mean, anything's possible. I don't think it's likely, but hey, given that we haven't heard any radio waves, maybe most of the life out there is around neutron stars, and why would they communicate with radio when, it's kind of like kind of trying to talk in a at a rave, so much noise you can't. That's not a good way of communicating.
Yep, got it.
So, and here we have.
Wait, you want to share?
Now I'm going to blow past a whole bunch of equations.
Lots of math.
Yeah, lots of math.
Oh, there's a nice structure one.
Yeah.
Let me share that.
Yes. And
All
this
right.
is.
Here you go.
This is the compositions of the layers. The crust, outer layer, has ions and electrons. Essentially, ions are simply nuclei without their, or without some of their electrons.
I thought it was more or less.
More or less, yeah.
Okay, all right.
But there's also a bunch of free electrons.
Okay.
This,
which makes sense. Okay.
This next layer in, electrons, neutrons, and nuclei.
Okay.
So not all of the electrons have whacked into all of the protons. So there's, again, probably mostly neutrons. Then the neutron proton Fermi liquid. So a very small percentage of electrons in this Fermi gas is a Fermi gas, but neutron proton liquid. So this is basically cores so crunched together that they still can't be cores. They just became a liquid. It's kind of like ice crystals melting into water.
Okay, we got a comment. Ready?
Sure.
Dawn, thanks for commenting. Remember Robert Ford, Dragon's Egg, alien life form from Neutron Star. Yeah. I have not read that. Have you read that?
Oh yeah, long time ago.
Okay. Right? Yeah, Robert L. Ford.
90s, I think. Yeah, I don't even remember much about it anymore, but yeah.
Dragon's Egg. Okay.
Yeah.
Worth looking up.
And
sounds interesting.
It's in one of my boxes in the storage site. Because I do have it. And then
should I share again?
Yeah, just it shows the inner core is quark gluon plasma ? Because they don't know. It's just what happens when you crush these things enough. Well, these things might happen.
Now I'm curious to know what Dragon's Egg claims the life. Oh, okay, let's see. It was the quake that reminded me, not sure why. Okay.
Yeah.
Well, that would have been a significant event in the life of the...
Right. And although I think it was the quake that allowed the life that was inside the neutron star to actually exit. This is decades old memory.
Got it.
Because I think they did theorize about the crust then, and that was a broken crust that allowed things out.
Okay.
Now, how they would escape that gravity, I don't know. And
could they crawl along the surface?
Yeah, and would they explode once they got out of the gravity? I don't know. I mean, I don't really remember. Yeah, I don't really remember.
Maybe Don will remember.
It's been decades.
Okay.
But yeah, I remember it being an interesting book, but fairly dense to read.
Okay.
but of course that was in the
Yeah,
90s. So
I
that
don't
was
think
a
I've
while
read
ago.
anything by Robert L. Forward, so
Yeah, I read
he's
a
gone
bunch
now.
of his
He's
stuff.
gone.
Yeah,
I remember. We saw him at conferences. I remember.
Yeah, yeah.
Always the vest.
Yeah.
Very colorful vest.
Yeah.
You want me to share again?
Magnetic dipole radiation. Oh, non-pulsing neutron stars.
Whoops, we got a. Huh. I wonder
Okay,
if we had a. Okay, if you can hear us, let us know. And if we went away, I think we're back though. Go ahead.
Yeah.
Do you want me to share?
Yeah.
Okay.
So apparently there are some neutron stars that don't pulse.
Interesting.
Yeah. It just and the spectra is radio emissions.
Okay.
There are some visible light, near infrared, ultraviolet X-rays, and gamma rays.
Yeah,
But
they're all
most
along the
of it's
spectrum.
X-ray. Yeah.
Oh,
Most of
X-ray.
it.
Okay.
X-ray. And spin down over time, they slow.
It's take a long time though.
Yes.
Okay.
But the rate of slowing changes
Okay.
over time, and there's again math in it. These are rotation-powered pulsars. So these are neutron stars, and this is the rotation versus the speed at which they're slowing down.
And Dawn came back with, do you want to see this?
Yeah.
So apparently these creatures from the neutron star were called Chila, intelligent creatures the size of a sesame seed who live, think, and develop 1 million times faster than humans.
Mm-hmm.
Chila.
Yeah.
Very interesting concept.
Yeah.
And heck, there's energy there, so,
yeah. Neutron stars can get faster, especially if it's pulling matter from a partner star.
Ah, okay.
Glitches and starquakes, we talked about those already.
Mm-hmm.
Anti-glitches, actually some glitches cause it to speed down. I think it's the same thing as a glitch, it just shakes it in a different way. Population and distances. Binary neutron star systems. Okay, we've seen a lot of, in fact, the easiest way to see a neutron star is if it's pulling matter from a companion and causing novas, because basically enough matter builds up on it that it blows off a bunch, but it still absorbs some of it. Now, one of the also very interesting things, and this happens more than we used to think, neutron star binary mergers. Basically, a binary star system that both become neutron stars.
Okay.
And they spin, they smack into each other, and the energy from that, they're saying, produces most of the heavier elements.
Okay.
The heavier
and the black
elements,
hole too, right?
Yeah. Oh, what does Thomas say?
Thomas says, are neutron starquakes detectable as gravity waves?
No, they're not big enough.
Good
they are detectable in the spin rotate, the spin timing. That's how they detect. That's how they theorize that. What causes that? The spin that's super regular suddenly isn't regular for a moment. No, but
so hiccups. Basically.
But the two neutron stars hitting each other,
yes,
they do cause gravity waves, and that's something that Anton talked about in his video today. But they say that almost all of the heavier elements, including a lot of the stuff that makes up life, like the potassium in us, was created by neutron star mergers and that explosion. That yes, supernova do create traces of those things, but not to the degree that they're present. So they're thinking that neutron star mergers created a lot of what makes us us.
Interesting.
And
we're still star stuff. I mean,
yeah, but so
maybe just different kind of star.
Yeah, so that's just kind of, so we owe our existence to two neutron stars blowing each other to smithereens.
All right.
And when they do that, though, what happens if they become heavier than 2.3 solar masses? Well, they could become a black hole.
Yeah, it sounded like from what Anton was saying that that's pretty much the
Mhm.
natural outcome of two of them
Right. Except
colliding.
that they don't always.
Oh, they don't always. Okay.
And that has some, that's causing some head scratching. So we don't know why.
What happens to them? They just make a bigger neutron star?
Yeah.
Okay.
They think that if it spins fast enough, that the pressure, the outward pressure of the spin allows it to have more mass. That so if they spin into each other and collide, if they do it wrong, they'll despin. But if they do it right, they'll add their spins to each other. They'll add the rotation to the spin.
Okay.
And it might get it spinning fast enough that you can have like a super massive neutron star.
It just won't collapse into a black hole.
Right.
Okay.
Now, neutron stars slow down over time.
Then they collapse into a black hole, right?
Probably. Can't say. Can't say for sure, but that seems reasonable.
Okay.
Because we haven't seen it happen.
Sounds like it's pretty hard to see anything.
Well, yeah.
In the neutron.
Yeah.
range.
Well, I would imagine that if it becomes a black hole, you'd have something similar to a supernova happening. Because I think the core would collapse, the outer part would collapse onto it, but might heat up enough to blow off the farthest, reaches of it. So you might get an explosion.
Okay.
Just like the easiest way to spot a black hole is by seeing the energy put off by the accretion disk. Because that stuff heating up enough because it's being crunched into each other and rubbing against each other that it produces heat.
You want me to share?
No, I'm just looking for the next.
Let me know when you're ready.
Okay.
Oh, that looks pretty cool.
Yeah, subtypes.
Here you go.
Rotation powered pulsar, which is what we call a pulsar. And it's just the rotation. Rotating radio transit. Pulsars which emit more sporadically and or with higher pulse to pulse variability. Now, usually with a pulsar, it's not the surface that's, there's no point on the surface, on the equator, that's producing radiation that pulses. It's the radiation coming out of the core. Or, out of the axis, out of the poles. So,
the picture kind of shows that, right?
Right. So it's not the fact that it's rotating. It's the fact that that axis is precessing, is doing this. And that's where it's the precession. We're not measuring necessarily the rotation, but the precession of that axis.
Okay.
As that beam goes past us. And there are one thing I saw was sometimes maybe they're on their side so that the axis is spinning while the thing is spinning around the axis. Probably happens in a collision like that. I don't know. I don't know that we've actually seen those. Someone who knows more about neutron stars would know that, but it's a logical conclusion that one of those happens somewhere. It would take just the right hit to cause that to happen. But the universe is big, and it's been around for a while. So chances are that there's some of those out there.
Quite a while.
Yeah.
Is that what they're demonstrating in that picture? And I think you can click on that and blow it up, right? Yeah. So if you don't mind, kind of.
Yeah. Here, let's bigify this some. Okay, magnetar is just a neutron star with a really strong magnetic field.
Got it.
Pulsar is, twin beams of radiation from their magnetic poles. They may not be precisely aligned with the neutron star's rotation axis, Oh, okay. So the magnetic poles aren't necessarily the rotational poles.
Okay.
Just like our magnetic pole on the Earth is not
Yep.
necessarily.
Yep. It's slightly off.
Yeah. And then, of course, there are 6 known neutron stars that are both magnetars and pulsars.
6.
Yeah.
Wow.
Yeah.
Fascinating.
Okay. How do I get this? I need to make this smaller, and I just need to go back.
Yep.
And click that. Okay. So magnetars,
let me go back.
radio quiet neutron stars. Some neutron stars are X-ray dim, and they're just possibly old. Possibly their spin is slowed down enough that, or their poles are just not aligned with us. X-ray pulsars are generally the beam that comes out of it hits the gas cloud around it, and that causes X-rays.
Okay. That's a pretty big list.
Yeah. Proto-neutron star is theorized.
What does it mean? Did they say?
Just something that's not quite a neutron star.
Okay.
Then there's exotic stars, and these are just ideas that people have had. Currently, a hypothetical merger of a neutron star and a red giant.
Wow.
Basically would have a layer of real matter on top of the neutron star matter.
Okay.
A quark
sounds exotic, all right.
Yeah. And probably there'd be a slow burn of the regular matter basically sinking in and compressing and becoming neutron matter. A quark star, hypothetically, we talked about it. If it's big enough, maybe it becomes a quark star without actually becoming a black hole. Electroweak star, a hypothetical type of extremely heavy neutron star, which the quarks are converted to leptons through the electroweak force.
Boy.
But the gravitational collapse of the neutron star is prevented by radiation pressure. Now, of course, this would be temporary because as it cools down, then it would be, so it'd be just on the way to becoming a black hole.
Okay.
But it could take millions to billions of years. But, and a preon star composed of preon matter. What the hell is preon matter?
Hypothetical.
Hypothetical point particles as the subcomponents of quarks and leptons. So what makes a lepton or a quark? Well, maybe preons. We don't have any evidence for them, but someone's done the math, and the math works. And so examples and so
that's a nice art involved with these.
Yeah.
That's cool. That is one thing we can say about this whole field. There's really beautiful things to see.
And
should I share that one?
The International Max Planck Research School has some stuff on the merger of neutron stars. And so, again, it's the same thing as we've talked about. And I'm once I'm done here and Pam's doing, what's up, what's going on this week, I will put a bunch of these in there because this is Chandra X-ray Observatory. Again, not real images, but these are what they believe certain neutron stars look like. And
when you share these, they should be clickable links in the chat.
Now, science has a good page on the physics of neutron stars. Unfortunately, hit the paywall.
Paywall.
Good magazine though. And this is just a wiki, and this is Britannica has a pretty good one. Not as good as the wiki. It's more succinct, but doesn't go into as many things. So if you want a quick look at it, Britannica has a good one, and I'll put that in there as well.
It's useful to see things from different perspectives.
Yeah. So
okay, was that it?
Yeah, I think that's
cool.
it.
All right, so if you have any more questions, definitely put them in the chat. All right, you want me to go on to this next section?
Yeah, and then I will, I'll do a bunch of these links into,
okay, good.
into notes.
So some stellar events this week. It is April 12th through April 19th. It's Yuri's Night, the World Space Party. And let's see, what do I have? Is this the one I have to share? I forget. I have a link there too. I'll share it in a minute. April 13th, the moon runs high. April 15th is the last quarter moon. April 18th, Mercury and Venus are in conjunction. April 19th, Friday night show. Well, we're trying to do like an eclipse recap.
Yeah.
So
and if we can't do that, I'll punt and do a Zooniverse.
Okay, cool.
Citizen science thing.
You can find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. What inspires you the most for this coming week? While you're doing that, I'm going to share this one too. This is, let me see if I can remember what the heck it was. Is that the space party? Yuri's Night?
Yes.
Is it? No, yurisnight.net is the.
Oh.
I'm trying to remember which one. Oh, I know, the free book, because I have some things here. Let's, because the one for the free book is very, very long. So I'll go ahead and talk to you about these things here. Here's the Yuri's Night one. And you can still send art to space. There's digital postcards. And you can send live regular postcards. This is the Blue Origin Club of the Future. I wanted to show you this again because it's quite a ways away. Nightscaper Photo Conference. It's going to be in September in Utah. Nightscaper.com would be a good place to start for that. There's the free book. That's the link that I shared, and it's offers out how things work at nasa.com. And you know, I'm sitting here going, I should probably get a copy of this book just so I know what in the heck he's talking about. Discover the little known secrets of space exploration NASA won't tell you. Could be interesting. Rocketown Comic Con is May 4th and 5th. 10 to 5 each day. And Lompoc, that's up there by the
Vandenberg Air Force.
Vandenberg, yeah. It's Space Force Base now. Yeah. The Space Race chess set is still trying to raise some money. I don't think they're doing real great yet. They've got 8 days to go. So if you want to support this, it does look kind of interesting though. I don't know that people are very much into the whole idea. I mean, well, I guess if you like history and stuff, you might be very interested in this. But it's a cool idea, and he's looking for some money, $30,000. Then there's this it's a automation conference in Chicago, May 6th through 9th, Chicago, Illinois. Sounds pretty cool. Robotics. See the pictures? Good stuff there. And we'd like to share with stuff anywhere in the world, so we'll have some different things in different places, including this one. Humans to Mars is the summit for 2024. See yourself in the future. This is May 7th through 8th in Washington, D.C. You can register now at exploremars.org. Yep, that's where we are. Do they have the location? The Jack Morton Auditorium, the George Washington University in Washington, D.C. Some of the people that they're going to have talking. Looks pretty cool. The agenda. I like stuff like this. We used to go to these a lot. Then there is this one here, the Global XR Community. And you know, I was trying to remember what XR means because VR is virtual reality. XR, I don't remember. If somebody knows, drop a comment for us. But there are a variety of these in different places, United States, June 18th to 20th. Oh, that's pretty close. Long Beach also. I just kind of found this recently, so I don't know too much about it. Then there's August in Singapore, October in Austria. How cool is that? Yeah, and they have a couple other things.
As well as an ad.
Yeah, or you can sign up. I think that might have been what that was. Yeah. Augmented reality is AR. VR is virtual reality. I don't really know what XR means then, I guess. All right, so if somebody knows, please tell us. And I thought this was just fun as a Target ad for, I think I found it on Facebook. Stomp Rocket Space Collection. Sounds pretty cool. Edwards Air Force Base is going to be coming back
extended reality.
Extended reality. Ah, okay.
So like My guess would be like putting like stats on something that you look at. Like you look at
Okay.
someone and it puts
All
their
right.
name or something.
Okay. Well, I can see it being useful like outside a plane. Oh, and here we have the meteor crater in Arizona, and this is this mountain, and this is this whatever city, any kind of thing. All right, so let's
It'd
go
be
back.
like a heads up display in your
Yeah,
eyeballs.
right. Heads up display. Edwards Air Force Base, the air show is going to be back in October of 2025. That is in California. North of us, though. We're near Los Angeles, so way north. And I thought this was kind of a neat ad for this magazine, Kids 12 and Up, as well as parents, the best science magazine. Newish every month, ad free, 100 pages. I guess you can get it in print or digital. And this is oyla.us. So yeah, most of these I get from ads on Facebook, and of course, the more I click on them, the more they show me. Yay! But they look like they've done some pretty neat things.
We should take a look at a issue of that, or so, just to see what it's like.
Yeah, why not?
Oh, and why not toss that link into?
Sure. Yep, I can do that. Copy. I just gotta find where we are.
Yep.
Oh, and Scott put it in here too.
Yeah, Scott had.
Excellent. Is that how you knew?
No, I actually looked it up, and
Whoops,
that's why that's why I didn't see him.
ER extended reality XR or XT
XR.
XR.
Yeah.
XR. Okay, cool. Let's see. Let me go back because I think I got one more. I just found this. This sounds really neat, and it's in Ohio, the International Women's Air and Space Museum, Friday, April 19th. And I wanted to include it instead of waiting until next week, even though I just found it right before the show, because it is going to be very soon. I think you want to take a look if you want to do this.
And my guess is that it's money because they say dinner.
Yes, I'm sure there's a little bit of money involved. But I really think this is a great place to go and find out more about this person, Jerry Mock.
Not bad.
No, it's not. It's not too bad. And they have so if you're in Cleveland, it's at the it's on the lakefront. They have North Marginal Road, Cleveland, Ohio. Here is Burke Lakefront Airport. I actually know where that is. A little bit more about the event. Yep, if you're a member, if you're a non-member, get your tickets and renew. So, yeah, good stuff. There's their local International Women's Air and Space Museum. And that's what I have for that segment.
Okay.
You can come back to us.
Here we are.
So let's see. Where are we on this? Go ahead. You read this part.
Okay. If you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, April 19th, where we'll do something. Our hope is to get people sharing their experiences with the solar eclipse. If not, I'll pull a Zooniverse out of my butt.
You were looking at one of them.
Yes. Unfortunately.
Kind of interesting, but
yeah. It's the latest up, but it's already 37% done. So, I was real tempted to just say that that's what we're going to do, and then
oops, we have to do something else.
Yeah, because we probably will.
Not entirely sure. Oh, Dawn's got you want to do it?
Oh yeah, Dawn says an eclipse recap sounds good. Yeah.
Okay, and if you're willing to be there with us, we're trying to get Cliff.
Yeah.
Although I think he's going to be moving again.
Yeah, he's traveling right now, so it's hard.
Well, he's landed in Florida.
Yep.
I think he's going to go to Tennessee, Washington D.C. next. Yeah. One of those two on the 18th. So the 19th, a bit iffy, maybe right now.
Yep.
So thank you, Dawn. Yeah, and who knows? Maybe we can find some other folks that have, because I've seen a lot of comments on Facebook that.
Yeah, if any of you got to see the total solar eclipse, or even like us saw partials.
Yeah. I'll start asking on Facebook. I'll say, hey, next week we want to get some folks coming in and talking about their experience of the eclipse. I know that when Cliff was in Frost, they had like clouds and clouds and clouds, clear for the eclipse, and then the sky just opened up and he was stuck at the airport for 36 hours.
Ouch.
Yeah, because he didn't want to get stuck somewhere else and not be able to get to the airport. So, yeah, adventures, right?
Mm-hmm.
Adventures. All right, folks. Anything else from you? Anything else from you?
Nope.
We'll see what happens next week. Hopefully, we'll do a recap on the eclipse.
Yep.
That sounds really fun.
If not, I'll pull some Zooniverse out of the air to do.
All right, folks. Have a really great week.
Good
And
night.
we'll see you next Friday. Bye.
Good night.